Welcome to this session on writing requirements for flexible systems. I'm Joe Casa, and I'm speaking to you from Adelaide, Australia. In this presentation, I'm going to talk about the context of a system, discuss systems of systems, then look at requirements for flexibility, mention some of the attributes of flexibility, show how capability drives requirements, touch on evolutionary acquisition, and then give you some examples of failures and successes, the lessons learned from flexible systems, draw some conclusions, and then take part in the discussion, questions and comments on the presentation and the material therein. This slide shows the system of interest as that red blob in the middle. The system of interest is going to interface with other systems, shown as the yellow rectangles, and each of those systems will interface with other systems, etc., etc. So, in the spatial domain, the system of interest interfaces with other systems, as shown here in this slide. And at the same time as the system you're developing is being developed, those other systems are also going parallel evolution. The colors represent different phases, and as you can see that at one specific period of time represented by that vertical line, the systems are in different phases, and that line will move. It's thus important to consider the temporal domain as well. So if you look at the system from those two perspectives, you can see that it's part of a set of other systems, which brings me to the term systems of systems, a phrase first coined about 1995 to cover the topic of complex systems, specifically systems that were not designed as a single system but seem to have evolved. Examples of this are permanent and temporary. Permanent or dedicated systems of systems tend to be airlines or national defense forces, whereas temporary or virtual systems of systems are multinational peacekeeping forces or a project team. The critical factor that's being recognized here is those systems are under continuous evolution. Here's my perspective on systems of systems. If you think of the metasystem, system, and subsystem hierarchy as a vertical view of a system, you can think of the system of systems perspective as a horizontal view. So here you can see that while systems A, B, and C constitute subsystems of the metasystem, in the same way as those lower subsystems constitute subsystems of System B, the horizontal perspective of System A, B, and C show up as a systems of systems view. The need for flexibility is being driven by extended operational lifetimes, decreasing budgets, we've got to make the systems work longer than originally intended, rapid changes in technology, national objectives and threats, instances where the technology is driving the change, and logistics issues in that we're trying to reduce the number of items in the spares inventory. So in terms of requirements for flexibility, what we're looking at are multi-purpose systems, and here we get into the issue of mission-specific as opposed to multi-purpose. For any specific mission, a mission-specific system is more effective. In general, flexible tends to weigh more, give you a reduced payload with respect to multiple systems. We're looking at types of missions, and then we're also looking at a system that will handle unknown missions and capability. We tend to be looking in a design to inventory environment, and we're looking for flexibility. And the example I tend to give is the Swiss Army knife. It's multi-purpose, but for any one of its blades or widgets, a specific tool will usually do the job better. So in considering requirements, the first thing we need to look at are the attributes of flexibility. They tend to be frames, or in the software world, table-driven software. For example, the table-driven software for telemetry display, if these parameters are passed to it, x-coordinate, y-coordinate, value, color, type, that's numeric or string, format, decimal point, lower limit, color, upper limit, color, blinking, etc., we can then use one subroutine to display any kind of information on a user interface in a single program or in other programs. So we've got a very flexible piece of code. In terms of hardware, if you've got a facility that is equipped with standard racks, it can be used for a multiplicity of purposes. Similarly with connectors, if we have a standard connector, we can use connectors from a variety of manufacturers. If we've got standards, then equipment can be used interchangeably. And the issues deal with, for example, do we put circuitry on the motherboard or do we use daughter boards? You've got to remember that one size may not fit all, and you've got to allow for innovation. So if we use a PC as an example, you can see that there's circuitry on the motherboard and there's slots to add other cards. These slots can be used to add features that were not available when the PC was designed, or better capability than currently exists. System level flexibility means parts from any manufacturer or many manufacturers can be used in many different scenarios interchangeably. So in terms of communications equipment, we standardize on frequency and modulation, and then anybody's can be used. Vehicles deal with load, range and fuel. In terms of ordnance, 9mm bullets will fit any 9mm weapon irrespective of who they come from. And so in order to end up with flexibility, what we need are standards. But flexibility has pitfalls as well. Sometimes the excess capability in the flexibility leads to problems when equipment is used out of context. For example, warriors tend to use new equipment in ways that were not envisioned by the designers. Now, while this is a tribute to the work of the developers to provide that capability, it nevertheless could produce embarrassing and costly technical problems. For example, some of the reliability and performance problems that plagued the US Air Force's F-1000 engine were due to the fact that the engine was overpowered and had a lot of resilience. It had been designed principally for speed, but when it was put in the F-15, the pilots found advantages in rapidly changing speed and submitting the engine to thermal cycles for which it wasn't designed and tested, and so it had a reputation for not doing very well, whereas in reality it was being used out of spec. In the traditional acquisition process, a system that met the requirements was implemented within a set of constraints. However, the set of constraints didn't include that of an architecture, so designers were free to build their system around any architecture. But in the age of design to inventory, the designers now have to limit their implementation to something exists within the relevant architectures. So the system engineer now has to identify non-existent capability within the architectural framework. And we do this with an iterative process in the following manner. We develop a set of operation scenarios or concept for the system, and for each item in the inventory we identify in which of the scenarios it can be used, and then when we're done we draw a table just like you can see here, and we use an X to signify that the inventory item has the capability that allows it to be used in the scenario. And this applies to system and components, or system of systems and systems. We then look at the rows and columns in the table. Inventory items or rows that have X marked in several columns are flexible items. Any row that's a subset of another row contains an item that is less flexible than the other row and is a candidate for phasing out unless there are specific reasons for not doing so, such as a much lower cost or additional capability that are not used in any of the scenarios. We then examine the capability of the items, and we use the total capability to postulate additional scenarios. Now, these additional scenarios are based on the evolution of technology, changes to national objectives and threats, etc. We add columns for the additional scenarios to the table. We put the X's in the appropriate places for the items that can be used in the new scenarios, and then we look at missing capability. And then we start the acquisition process for systems that would contain the missing capability. And this process is an evolutionary acquisition paradigm in which the system of systems perspective is maintained. Now, at the same time that we're in this process of examining the capability and then ordering the equipment to fill the gap itself is changing because other systems are coming online. Remember that temporal diagram back at the beginning of the presentation? And other systems are phasing out. So the gap isn't constant. It's dynamic. And what this means is we really have to make our decisions as to what our requirements are in a just-in-time manner so that we freeze the requirements just in time to have them built. So here we are working back from the solution, figure out when we're going to need it, how long it's going to take to build it, and that's when we freeze the decision. And when we do this, we maximize the don't care aspects of the system, and we provide flexibility, but on the other hand, we're also introducing risk. Traditionally, we're taught when you start with the requirements, any solution is open and not to fixate on a single solution. And that's a sort of forecasting approach. I tend to work with a backcasting approach, which is to identify the user requirements. That's the concept of operations. And then I visualize the system in operation and develop the system requirements from that and prioritize the requirements. But there are many things that I don't need to decide at this time. Now again, there's a risk. So for example, I need a communications path if I'm designing a communications link between Adelaide, Australia and a conference in the UK, but I don't really care whether it's satellite or cable or fiber, and so I don't need to decide that at this time. I'll decide that later. I also identify what I don't want and what I don't care, and then I flag the decisions at a timely manner in which they have to be made, and then I proceed from there. So I don't make my decisions until I actually need to make them. This means I have to have an effective change control process, and I have to be working within an organization with a higher capability maturity model level. However, I also have to look at the external factors that might affect my project and the design decisions, and this fits in very nicely with the PRINCE2 management method. And I mustn't fixate on a single solution. I've got to be flexible enough to know when I've reached the point of diminishing returns or the solution that I'm looking for is not the correct way, and to be able to think about alternatives. So I've covered the context of the system, systems of systems, some requirements for flexibility, attributes of flexibility, shown how capability of the inventory can drive requirements, and shown a little bit about evolutionary acquisition. And it isn't easy, but now I'd like to share some examples of successes and failures. So I'm going to show examples of systems from the macro to the micro. The Luz SEGS-1 project, the NASA Space Shuttle, the Sergeant York Air Defense Gun, the Standard Central Air Data Computer, the RCA COSMAC 1802 microprocessor, and the new Joint Strike Fighter aircraft. SEGS-1 is an example of a situation where there was total lack of interface specifics and unknown tolerances. Back in the mid-80s, Luz built the Solar Electrical Generating System number 1, a solar field that generated 16 megawatts of power from the sun. It was a set of parabolic trough reflectors that focused oil at the center in which a pipe was placed. The pipe contained oil that was pumped through. The oil was heated by the sun. The hot oil went through a heat exchanger and heated water to steam, and the steam drove a turbine to generate electricity. The R&D was done in one country, and the installation was on the customer site halfway around the world. And the focus of this talk deals only with the solar electrical generating field. And when I say halfway around the world, I mean it. The design was done in Jerusalem, Israel, and the installation was in the Mojave Desert in California, just outside Los Angeles. The system had about 600 mirrors to be spread out over a field the size of a football pitch. Each mirror was about 40 meters long. There was an unknown electrical magnetic environment, and we had cables running between the mirrors that were buried underground. There were mechanical electronic interfaces. We had union labor at the installation site, so everything had to be robust. There was no land space for test facilities in Jerusalem, so we couldn't build full-size equipment. And there were major prototype problems. The motors were blowing the SCR controllers. The interfaces didn't have the fan-out capability when I inherited the system. We had language difficulties. Israel's a nation of immigrants, so we had people who spoke Hebrew, French, English, Romanian, and Russian, but not everybody spoke the same set or the same subset. So we were having meetings when there were people in the room who could not understand what was going on, so every now and again meetings would break up with interpretations. There were logistics difficulties. At that time, Jerusalem was at the end of a long pipeline, and there were ordering delays on parts, so if we thought we needed something, we had to shotgun an order. And it was a startup company on tight finances, so there were minimal resources. If that wasn't enough, the parabolic trough reflectors only had elevation control. They were laid out in a roughly north-south alignment, and they could only move up and round. There were wide tolerances on the north-south alignment of the mirrors, and the mirror pointing requirement was plus or minus 0.2 of a degree. And there were no vibration specs on the mirrors, and the sun sensors were mounted on the mirrors. And there was also no sun sensor specification other than relative outputs, crossing points. So the position had to be computed based on a set of variables or a set of parameters on which there were unknown tolerances. And yet the mirror had to point within an accuracy of plus or minus 0.2 degrees, because if it didn't, the pipes would be off focus, and when they're off focus they radiated heat instead of absorbing heat. And the result was a success. The control system worked the first time. We saved $300,000 by using a microcomputer instead of a mini computer. It was in there on schedule, and the only problem that the field had was a single hardware connector. We had been using flexible cable in Jerusalem, and the cables that ran between the local controllers were assembled in America, and they used a semi-rigid cable. Our flexible cable had been used with push-on connectors to simplify the union installation in the field. However, the push-on connectors were not strong enough to hold the semi-rigid cable in place because it eventually popped off. But as soon as we found that problem, they were fixed in place and everything went well. However, there were problems with the sun sensors, and position anomalies arose, and we found out that it was because the sun sensors were slowly going blind. Details of how I achieved this success are in the paper, and it took me 15 years to figure out what I had done to make this project a success, and I'm still documenting it. The problem with the sun sensor dealt with a don't care scenario. If you see the picture of the diode and sun sensor on the screen, you can see that there's glue in front of the photodiode. Now in manufacturing, it's a lot easier to assemble that diode if you don't worry about glue and just slop it all about. After all, it's a transparent glue. There shouldn't be any problems, right? It's a lot harder to assemble it if you make sure that you don't get glue on the front. What happened was the photodiodes have the sun's rays focused on them. They get hot. We didn't have a temperature spec on the glue, and after months of being hot, it slowly went opaque, and the sun sensors slowly went blind. Here's an example of when a don't care situation will hit you. It can be thought of as adding an additional component in series in the reliability path. The space shuttle is an example of an approach to designing a flexible system based on the assumption that one size fits all. Concerned about the cost of expendable vehicles, in an era when spaceflights were anticipated to become commonplace, NASA intended to reduce costs by designing a single reusable vehicle. The result was an expensive vehicle and not entirely reusable, since expendable parts, boosters and fuel tanks are employed. And experience has shown that one size does not necessarily fit all, and a more flexible solution may be expendable cargo carriers and a small reusable manned vehicle based on the single stage to orbit prototype. This vehicle would have the support requirements of a commercial passenger jet aircraft. However, such a solution might still not be politically correct, since NASA has a large investment in manned mission support. And in a sense, NASA does launch both the shuttle and expendable vehicles because they've implemented a mixed solution, but at a greater significant cost than a system designed for a mixed scenario. Once on-orbit docking capability had become routine, a mixed launcher solution became very viable from the technical perspective. Yet the political impact of the reduction in support staff is a pertinent issue that seemingly remains. The shuttle fleet is aging, and no replacement program has been announced, even with a commitment to support the International Space Station. The Division Air Defense Gun, Sergeant York. This program was initiated by the U.S. Army's recognizing the need to replace the aging M163 20mm Vulcan anti-aircraft gun and the M48 Chaparral missile systems. The new self-propelled anti-aircraft gun system was to be based on the M48A5 tank chassis, using as much of the off-the-shelf equipment as possible. So within the constraints of using as much off-the-shelf equipment as was possible based on the M48A5 tank chassis, two designs were submitted, one by General Dynamics and one by Ford Aerospace and Communications Corporation. The selection of contractor was made in 1981, and the first production vehicles were delivered in 1983. The vehicle had twin 40mm guns mounted in a new box-like armored turret with both tracking and surveillance radar fitted on the top. These could be folded down to reduce overall height. There was a roof-mounted sight incorporating a laser rangefinder for the gunner. There was a panoramic roof-mounted periscope and fixed periscopes for the commander. And the radar was a modified version of the Westinghouse APG-66 system used in the F-16 Fighting Falcon. But alas, the gun had problems. The radar could not track low-flying targets due to excessive ground clutter. The radar couldn't distinguish between a hovering helicopter and a clump of trees. When tracking high-flying targets, the radar return from the gun barrel tips confused the fire control system. Turret traverse was too slow to track a fast-crossing target, and the ECM suite could be defeated by only minor jamming. And if that wasn't enough, the use of the 30-year-old M48 chassis design meant that the vehicle had trouble keeping pace with the newer M1 Abrams and the M2, M3 Bradleys, the very vehicles it was designed to protect. These problems proved insurmountable, and in December 1986, after about 50 vehicles had been produced, the entire program was terminated. Turning from an American failure to a British success, the SCADC project was one of about a dozen standardization programs initiated in the late 1970s by the United States Department of Defense in its desire to obtain substantial reductions in equipment lifecycle costs through the wide use of digital common modules in aircraft. It was thought that SCADC, because of the complexity and accuracy requirements of air data computation,
would be a replacement for existing analog equipment.
In addition, the SCADC program required the delivery of up to 150 units per month shared between two winning suppliers in a continuously competitive leader-follower arrangement. Two of the three largest U.S. suppliers of airborne air data systems, Honeywell and Sperry, declared the concept impossible and declined to bid despite the potential of $500 million of business. GEC Avionics were interested in the business and designed and built a SCADC in a replacement form-fit function for the then existing analog components. The system was a modular core set of standard air data computer modules made extendable by the use of the 1553 data bus. The ability to replace old for new in around 30 minutes on thousands of the older inventory aircraft, raising the mean time between failure rates from about 100 hours to greater than that of the aircraft lifetime, and at the same time equipping them for plug-in new attack systems via the 1553 data bus, was a significant technical innovation. However, it also had the effect of putting many logistics people out of work overnight. And so when the first prototypes were demonstrated, a huge effort was launched in Washington by the logistics fraternity to have the project cancelled. This was supported by much of U.S. industry, who could see an outcome that depleted a large portion of their diverse business with the danger of much of it going overseas. Although the SCADC programs continued, the implementation in service was delayed for up to 2 years. Another casualty was all that the other standardization programs fell by the wayside. By 1998, 6,000 units in various configurations had been sold, including a version now modified into a digital flight control system adopted by the U.S. Navy for the F-14. It was the most widely used digital system and most reliable in all aircraft in the Gulf War. The program was arguably the most successful of any airborne equipment supply program in the history of world aerospace, and 100% of the production units came from the UK source, the leader-follower concept being abandoned. It was estimated that by the time GEC Avionics received the third or fourth order for the production units, the direct defense savings exceeded $500 million. The RCA COSMAC microprocessor was the first 8-bit CMOS microprocessor in the mid-1970s. It was ideal for environments in which the low power and other characteristics of CMOS were desirable. However, it was less than a success. The hardware circuitry was simple to use. However, the software architecture was extremely flexible. It was so flexible that almost any register could be programmed to serve any function. Most people ended up using the device in fixed configurations and did not take advantage of the flexibility provided by RCA. And the picture you can see there is of the ELF prototyping unit. The Joint Strike Fighter is a multi-role fighter optimized for the air-to-ground role, designed to affordably meet the needs of the Air Force, Navy, Marine Corps, and allies with improved survivability, precision engagement capability, the mobility necessary for future joint operations, and the reduced life cycle costs associated with tomorrow's fiscal environment. The JSF is to benefit from many of the same technologies developed for the F-22 and will capitalize on commonality and modularity to maximize affordability, at least in theory. The United States Navy is looking for a multi-role stealthy strike fighter to complement the F-18E. The United States Air Force is looking for a multi-role, primarily air-to-ground fighter to replace the F-16 and A-10 and to complement the F-22s. The Marine Corps is looking for a multi-role short takeoff vertical landing strike fighter to replace the AV-8B and the FA-18. And the Royal Navy and the Royal Air Force are looking for a supersonic STOVL replacement for the Sea Harrier and the GR-7. The aircraft is being built using a concept demonstration philosophy. 2 teams, shades of Sergeant York, Boeing and Lockheed Martin. Each of them are extending a vehicle that they already have. So each team is going to build 2 aircraft to demonstrate the technology and critical system characteristics, commonality, modularity for an affordable family of multi-service variants, successful short takeoff, vertical landing, hover and transition, and satisfactory low-speed carrier approach flying and handling qualities. So the aircraft already comes in 3 variants. The United States Air Force is $28 million version, the Marine Corps and Royal Navy $35 million version, and the U.S. Navy $38 million a plane. Cost commonality is projected in the range of 70 to 90%. Parts commonality will be lower, but the emphasis is on commonality in the higher priced parts. So what lessons can be learned from flexible systems? Well, the lessons from the DIVAD. Integrating three systems produced an array of technical and operational test difficulties that ultimately led to its cancellation. All radar are not equal. There is a need for domain expertise when attempting to use capability outside its original environment. After all, the aircrew must have noticed the effect of operating their radar at ground level. They just didn't tell anybody, or they didn't tell the right person. And there was the failure to consider the system of systems changes in the other systems. The vehicles that it was supposed to protect were going to be faster than itself. At that point, there should have been a change. There was a focus on a single solution. On the other hand, 4 successive generations of upgraded U.S. forward air defense systems from Mauler to Roland to Sergeant York to ADATS were all cancelled at a total cost of more than $6.7 billion over a period of 30 years. So my question is, what does this mean in an evolutionary acquisition paradigm in an era of extending systems' operational lifespan? The examples here reinforce the lessons learned from other programs. Programs don't fail because the requirements change, and by failure I mean cancelled or incur more than 60% cost or schedule overruns. The tasks and the products and the processes to minimize that failure exist. They're all there in those old mill standards. Programs fail because of poor requirements engineering management and failure to manage change. Failure to reevaluate requirements in the context of changes in needs, technology, and paradigm. For example, look at air power and battleships. Air power sank battleships. Look what the Japanese did to the American battleship. And look what guided ordnance is about to do to surface ships. Another lesson learned is in evolutionary acquisition, it focuses on the application, not on the real needs. For example, let's take a look at manned aircraft. In World War I, they provided the ability to see over the horizon and bring back information about enemy dispositions. Well, the enemy were doing the same, so each side had added guns to stop the enemy from bringing back information. And what happened then was there was a branch into fighter aircraft in which the fighter planes went up and fought fighter planes, and there was really no furtherance of the war effort. But those same guns allowed for ground support, and ground support led to ordnance delivery, both on the trenches and behind the lines, and the whole thing led to specialized types of aircraft. So we've got fighters and bombers. In these days, when we've got computing power, expert systems, artificial intelligence, etc., we really need to sit back and ask, what are today's real mission requirements, and can they be met without manned aircraft? In conclusion, writing requirements for flexible systems is not easy. It's also pointless unless effective change management tools are developed. History repeats. I'm predicting the Joint Strike Fighter is doomed to cost and schedule overruns due to lack of change management tools, and it may also be doomed in the threat environment due to the failure to recognize there's a paradigm shift in guided ordnance. One size does not fit all. Several may be required. I hope I've given you something to think about. At the time of preparing this, I'm planning to phone in and take questions live, but if that doesn't happen, I'll take questions and comments through email, either at the address shown here or at the address listed on the paper in the proceedings. Thank you very much for taking the time to listen to this presentation.